So the last few questions in the homework from section 2.2 involve a type of equation which is very poorly named as homogeneous equations. I say poorly named because the word homogeneous we're going to use to mean something else for the rest of the course. This is the one place where homogeneous doesn't mean what it means everywhere else. Okay? The word homogeneous to me means somehow everything is the same, right? It's homogeneous. So anyway, what these equations are first order differential equations where the derivative of y with respect to x can be written as a function which is a rational function in x and y. So it's a polynomial in x and y divided by a polynomial in x and y. But more so, those polynomials have the same degree in every term. This is first degree in x, this is first degree in y. If you had a plus a constant here, that would not be homogeneous because the plus a constant would be a degree 0 term. It would be a constant, not a linear piece, right? Now, maybe this would, you could do ones where this is an x squared and this is a y squared, or an x times y, something that would be quadratic. But if one thing is quadratic, then everything would have to be quadratic, both the top and the bottom. This is linear in x on the top, linear in y on the top, linear in x on the bottom, linear in y on the bottom. It's the same. Every single term in this fraction is a linear function of either x or y. Okay, and that's what makes it homogeneous. Now, this is not a separable equation. However you try to get the x's and y's separated, you will never end up with just x, some function of x times dx, and some function of y times dy. It is not separable. However, we can do a substitution and turn it into a separable differential equation, which is why they sort of stick it in the homework section here. It's not even part of the text. It's just, oh, look at this if you do this stuff. So anyway, it's not the most important thing out of this section, but it is curious to show how you can use some algebra to take something that's not separable and turn it into something that is. So here's what we're going to do. We're going to take this equation, this right-hand side, and we're going to multiply that fraction by 1 in the form of 1 over x divided by 1 over x, essentially divide top and bottom by x. So the x divided by x is 1, the y divided by x is y over x, and likewise this x divided by x is this 1, and this minus y divided by x is that minus y divided by x. Okay, so all he did was some algebra to change this left-hand side into this. Now, I'm going to do a substitution, and this y divided by x I want to be v. So if v is y over x, I can solve for y and say that y is going to be v times x. Then I can implicitly differentiate this side, this equation with respect to x, and get that dy dx is, now this is a product rule here, so this is going to be v times the derivative of x plus x times the derivative of v. But I'm taking the derivative with respect to x, so the derivative of x with respect to x is 1. So here is v times 1 plus x times dv dx. So I just took the derivative of both sides here. So now I'm going to substitute this information back into this equation. So the left-hand side, dy dx, is replaced by all of that stuff. That's what I have written right here. And then the right-hand side, this is a 1 plus v on the top and a 1 minus v on the bottom. So there's that equation right there. Now I claim this is separable. So what I'm going to do is I'm going to take the v, move it over to the other side. There it is. And so now I've got this function of v on this side, that function of x on that side. But if I multiply by dx, okay, so I got to move the x and the dx over here, and I got to move all these v's over there. So first thing I'm going to do is get this into a single fraction. Get this into a single fraction here, so get a common denominator, and then just do some algebra, multiply that out. Anyway, this stuff turns into a 1 plus v squared over 1 minus v. So then when I multiply both sides by the reciprocal of that to get it over here, that flips upside down, the x comes in the denominator, the dx goes in the numerator, and I have it separated. So, integrate both sides. Side is probably easy enough. That's just going to turn into a log of natural log of x, log of absolute value of x, natural log of absolute value of x. There we go. And this side I'm going to split up into two integrals. The first one's an arctan. The second one, there's a u substitution with u equal to the denominator. So then du would be 2v dv, so I'm missing the 2, hence the half, and I end up with a 1 over u du, which is the natural log of absolute value of u, but I don't have to worry about the absolute value because in this case u is equal to 1 plus v squared. 1 plus v squared is never negative, so the absolute value is irrelevant here. And then I can substitute back in because v, after all, was y over x, and I should not have a v right there. And now the v is gone. So yes, we just substituted for that v y over x, and for this v right here y over x. And there we now have an equation which is the solution, the general solution to that differential equation. It would be pretty much impossible to try to solve for y, but if you had an initial condition, if you knew a value of x and a value of y, you could plug it in and solve for c. Okay. There's a couple of these problems at the end of the homework section from 2.2 for you to try. The process is exactly the same as what I illustrated here. So good luck with those.